Continuation of the topic. Last topic we discussed about the buffer solution. Now, how to construct a pH curves, like when acid and alkali are reacting with each other. So we can construct a pH curve which shows a change in the pH when acid is added to alkali or alkali is added to an acid. So first what we will do, we'll measure the initial pH, because when we measure the initial pH, we can identify like what should be the starting point. Then we are adding a small amount of alkali, then stir, and once the acid and alkali neutralize each other, the pH will be 7. If we add too much alkali, then the solution will turn alkaline. So example, if we are sketching a graph or a reaction between a strong acid and strong base. So strong acid, the pH is less than 2. So it will start with a value which is less than 2. Where strong base, pH 13 or greater than 13 or 14, equal to 14 or greater than 13, that will be for strong base. First thing, we will find the equivalence point. What is the equivalence point? When the mole ratio and the volume ratio is same, we call that as equivalence point. Like example, when we write the equation between hydrochloric acid and sodium hydroxide, so HCl plus NaOH. When we construct this equation, when we complete this equation, HCl plus NaOH, it will give NaCl, sodium chloride, plus water, which is H2O. What is the meaning of equivalence point? It means when the mole ratio according to equation is equals to volume ratio. Like the mole ratio according to equation is 1:1. So if we are taking 25 cm cube of HCl, when we add 25 cm cube of sodium hydroxide, that point, when the mole ratio and the volume ratios are same, we call that point as equivalence point. And at equivalence point, the pH will start to change. Before that, negligible change is there, even though you can see we started with a strong acid in a container or a flask, we have HCl, which is a strong acid. Now we are adding an alkali. Even though we are adding an alkali, but you don't find any change in the pH. Why there is no change in pH? It shows that this region, a solution, is acting like a buffer. It is resisting the change in pH. Once the mole ratio and the volume ratios are same, equivalence point we reach, that time you see a drastic change in a pH. What it shows that acid is neutralized by an alkali. And if we add further, then the solution will become alkaline because all of the acid is used up. So the important thing, the feature, the characteristic which you should remember is when you're reacting strong acid with a strong base, this vertical part is from 3 to 9. So how you'll work out, how you will solve this question, if I say you was having 10 cm cube of HCl and you are adding sodium hydroxide, because it is a strong acid, so it will start with a pH less than 2 and it will end at a pH more than 13. If we are taking 10 cm cube of HCl and we write the equation for reaction between hydrochloric acid and sodium hydroxide, so it will form sodium chloride plus H2O. So what is the equivalence point? Because the ratio is 1:1. So at what volume I'll get the equivalence point? If I take 10 cm cube of acid, I should have 10 cm cube of alkali or sodium hydroxide. And this vertical part where at equivalence point from 3 to 9. So what you will do, you will mark your scale, because in exam you don't have the complete marking, like axis may be marked, but you have to sketch this or complete this titration curve. So you will have the mark like example 5, 10, 15, 20. So 10 is the equivalence point, and the equivalence point for strong acid and strong alkali, the vertical portion is from 3 to 9. So first what we will do, we'll draw a line from 3 to 9 for this vertical portion. When the pH is 3 till the pH 9, we'll draw this line. And we know we have to end around 13 or 14. So we'll make a curve till 13, 14, and our start is about 1 or 2. So we'll join this. This is how you sketch. The important thing is to remember the vertical part for strong acid and strong base, which is from 3 to 9. Is it clear how to sketch this titration curve for a reaction between a strong acid and a strong base? Any doubt in this part? If you're having a reaction between a weak acid, if a reaction is there between a weak acid and a strong base. So first, because it's a weak acid, so it will have a pH more than 2. Example, you can start with 3. And strong base, so it will have pH greater than or equal to 13. So these are the indicators which you can identify from the question. And the vertical part, the vertical portion is from 7 to 9. So from 7 to 9, we have vertical portion or about 6.8 to 9. So what we will do, we'll sketch in the same manner. But you can see the here, because what happened, this region is actually a solution, a buffer solution is formed. That's why the curve is not like this, it's in other way around. Reason for that, when you are adding a limited amount of alkali to an excess of acid, so you will have a salt and the weak acid. So when you have a solution, weak acid and its salt, that's why it will act like a buffer in this range, this region. So vertical portion, if you want to sketch a graph, complete this. First, you should know the volume at which this vertical portion will occur to find the equivalence point. To find the equivalence point, if we are taking equal concentration of acid and alkali, say ethanoic acid is reacting with an alkali, so sodium will take position of hydrogen, it will form sodium ethanoate plus water. So again the ratio is between them is 1:1. Example, if ratio was 1:2, this is not 1:2, but if it was 1:2, then if you are taking 10 cm cube of acid, how much alkali is needed? You need 20 cm cube. So equivalence point will be there when you add 20 cm cube of alkali, not 10. But again, this example is ratio is 1:1. So when 10 cm cube of acid is there, 10 cm cube of alkali is needed. Or if you have 25 cm cube of acid, then you need 25 cm cube of alkali. So you will draw the vertical part first. It's about from like 7 to 9. And as you can identify, it was a weak acid. So it can start pH more than 2. So example, pH 3. And alkali, which was having pH 14. So you will join these points because you want to end till 13, and you started with 3, or it can be any according to the question, but if you sketch it will be more than 2. Same way, if we are carrying out a titration, from reaction between a strong acid and a weak base. So if a strong acid is there, then the pH will be less than 2, and weak base is there, pH will be less than 12. So we should end around 12. So what will the vertical part? It's from 4 to 7. So first we'll draw at equivalence point 4 to 7 and join the starting position and the ending, and that will be the curve. For weak acid and weak base, there is no vertical part. Why there is no vertical part? Because for its very small range, the pH change occurs. So that's why this part is not exactly vertical. Because it will start around 3 and it is ending around 10 or 11. So it's different. When it completed, it's not like a vertical part, it's curve still. So it's difficult to sketch the graph for weak acid and weak base. So we can sketch easily the graph for strong acid, strong base, the vertical part from 3 to 9, for weak acid and strong base from 7 to 9, and for strong acid, weak base from 4 to 7. Now, what are indicators? Indicators are also weak acids which show a color change according to the shifting of equilibrium. Like example, you have an indicator HIN. Here is a journal representation of indicator which decompose into IN minus and H plus. So this molecule is like example color A, and the ion of indicator is color B. So if it is acidic medium, if we add acid is added, or if more hydrogen ions are there, equilibrium will shift toward left hand side. So color A will be more. Like color A can be any color. It can be red, it can be green, blue, depending on the type of indicator. Same way, if we add an alkali, so adding an alkali react with hydrogen ion, reduce the amount of hydrogen ion in the mixture, which shift the equilibrium towards right hand side. So what we'll get more, we'll get color B more. That's why indicators show a different color in different mediums. And at a certain pH, the indicator will work if the pH range of indicator lie within the vertical part of a titration curve. Because in that part, the pH change is rapid, or changes hydrogen ion concentration is rapid. So it's easy to use those indicators. For example, as you can see, only use phenolphthalein in a titration with a strong base, but not with a weak base. What is the reason why we cannot use phenolphthalein? This is a pH range for phenolphthalein. So using a data booklet, you don't have to learn or memorize the pH range for the indicators. Data booklet will be there. So you can use a data booklet and identify the pH range for the indicators. Example, if this phenolphthalein is having a pH range from 7.5 to about 11 or 10. So if you are using a strong, if the reaction is there, because in this part, it is showing a color change. So if the reaction was there between a strong acid and strong base, or weak acid and strong base, then you can use phenolphthalein, because this vertical part will be there. If it's a strong acid, the reaction, it will start at position A and it will follow the vertical position, and then so vertical part will be there, and the phenolphthalein pH range lie within this vertical part. If we are using a weak acid and strong base, again the pH range, because this is a pH range at which the phenolphthalein show a color change. So the vertical part, what we'll check the vertical part, and we'll check the range of that indicator. So range of that indicator must lie within the vertical part. If it's not in the vertical part, it will not be effective indicator. Because what happened, for example, if I'm using phenolphthalein for a weak base, but you can see this is a pH range at which the phenolphthalein show a color change. So this phenolphthalein, when we are still adding a weak base, this region is within the pH range of a phenolphthalein, so it will not show a color change. Its color change will only occur, the color change will occur after this part. Like example, if originally it was colorless, it will show a color change within this pH range. Same way, if we are using a methyl orange, so methyl orange is best when we are titration with a strong acid but not with a weak acid, and the color change, it is red in acidic and yellow in alkaline. And you can see this is the range, the pH range of methyl orange. So for strong acid it is useful, but if you are using for weak acid, this weak acid, the pH, the vertical part is not in the range of the color change for methyl orange, so it is not suitable. So whenever you are selecting an indicator, how you select an indicator, you check this vertical part, and you check the pH range of indicator. Every indicator is having its own. If that vertical part, if the pH range lies within this vertical part, then you can choose that. Or it is also acceptable if one part is inside and one is outside, that's also acceptable. But the best one is which is having a pH range within the vertical part. But if one part is out, one is in, that is also acceptable. It is accepted in exam as well. But if the pH change is totally, like the 2 points for indicator range are out of that vertical region, not a single point lies in the vertical region, so that indicator is not suitable for the titration. Is it clear? Discussion? This explanation of selecting a suitable indicator. Now some questions related to this acid-base equilibria to understand this concept of titration curve, as well as how the questions are there in exam. The first one is related to organic chemistry, so I will not discuss that part. The second one is also, it's the test for the OH ion. We'll start with part C. So in part C, the acid dissociation constant Ka of a lactic acid is 1.38 exponent minus 4. A lactic acid is given, this is a lactic acid formula that's given. Write an expression for dissociation constant of a lactic acid. So we have to write expression here, like the expression in terms of Ka. So for lactic acid, dissociation constant for lactic acid, so it is Ka is equals to, because if I write the equation first, so it is CH3 CH bracket OH COOH, that is lactic acid. But when it will dissociate into CH3, CH bracket OH, COO negative and H positive. So when we write the product divided by reactant, the dissociation constant, so it will be CH3, CH bracket OH, COO negative, H positive, and divided by the concentration of lactic acid, which is CH3, CH, OH, COH. The next part they ask, state whether a lactic acid is a stronger or a weaker than ethanoic acid, and quote the data from page 18 of a data booklet to justify your answer. So what you will do using a data booklet, you will check the dissociation constant Ka. When you check the Ka for ethanoic acid, dissociation constant for ethanoic acid using our data booklet, it is 1.7 into 10 to the power minus 5. And in this question, the dissociation constant, or this is for ethanoic acid. When you check the data booklet, you can identify the dissociation constant for lactic acid is 1.38 into 10 to the power minus 4. This is for lactic acid. Which one is higher value, 1.7 exponent minus 5 or 1.38 exponent minus 4? Which value is higher here? So lactic acid value is higher. So what it shows, if dissociation constant is higher, it shows that the lactic acid is a stronger acid as compared to ethanoic acid. And you can quote the value for dissociation constant and compare and mention that Ka for lactic acid is higher as compared to ethanoic acid value. The next part, calculate the pH of 0.1 mole per dm cube solution of a lactic acid and giving your answer to 2 decimal places and state 2 assumptions. So first thing, we have a lactic acid and we know the concentration of the lactic acid. So if this is a lactic acid, so what is our assumption? Like this is the original concentration of a lactic acid, the original concentration of hydrogen ion and lactate ion will be 0. But at equilibrium, if a concentration of lactate ion and hydrogen ion is X, then concentration of lactic acid will be 0.51 minus X. But we always neglect this X. Why we neglect this X, 0.15 minus X? Because our assumption is that dissociation is negligible, like it does not dissociate completely, and the dissociation constant of a lactic acid is also with you. So you can just substitute the values and get the answer. So this is, I think 1.38 exponent minus 4. That's a dissociation constant of a lactic acid. Equal dissociation of lactate ion and hydrogen ion is same. So X and X. And 0.15 minus X. But what happened? The X is negligible, so we neglect that. So instead of writing 0.51 minus X, I can simply write 0.51. This 0.51 is divided, other side it will be multiplied. So 1.38 into 10 to the power minus 4 multiplied by 0.51 or 0.15. You will get the this concentration square, then take a square root, you will get the value of X. What's the final answer for X first? X, because X is a concentration of hydrogen ion. And after getting a concentration of hydrogen ion, pH is equals to minus log of hydrogen ion. What's the concentration of hydrogen ion? 1.38 exponent minus 4 multiplied by 0.15. Then take the square root. 4.55 exponent minus 3. And then take the square root. Sorry, that's you took the okay, you took the square root. So that's a hydrogen ion concentration. Then find the pH. So pH is equals to minus log of hydrogen ion concentration. Substitute the value. You got 4.55 exponent minus 3. 2.34. So 2 decimal places is a pH for this solution. Then what is our assumption? Our assumption is that the first one we already mentioned in our calculation, that our first assumption was we assume that the dissociation for the lactate ion is negligible, like this x value of x is very small. Second thing, because these acid and alkalis are in aqueous solution, so what is our assumption here? We always assume that all of this hydrogen is coming from acid, like the water molecule does not dissociate, but in practical the water molecules also dissociate. So this hydrogen can be uh, from water as well, but our assumption is that the concentration of lactate ion and hydrogen ion is same, or all of the hydrogen which is hydrogen ion which is present in the solution is due to the acid. Is it clear? The two assumptions, one is assuming negligible, very small dissociation for the molecule. The second one, all of the hydrogen is from acid, no hydrogen from water. Or you can also say the concentration of this ion, lactate ion, equal to concentration of hydrogen ion. A buffer solution with a pH 4. Any doubt in the previous question? If you have any doubt, you can ask. I will repeat that. Any doubt in this last question? A buffer solution with a pH 4 is prepared by using a lactic acid and sodium lactate. Calculate the mass of a sodium lactate that should be dissolved in 1 dm cube of 0.1 mole per dm cube solution of a lactic acid to make a buffer solution of pH 4. A sodium lactate has a molar mass of 112. So first thing, using the hydrogen pH, we can find the hydrogen ion. And from hydrogen ion, because the dissociation constant is already known, the concentration of the lactic acid is known, so we can find the concentration of lactate ion, sodium lactate ion or lactate ion. So first thing, what we will do, we will find the hydrogen ion concentration. The pH is given. So using the pH, I will first find the hydrogen ion concentration. So pH is equals to minus log of hydrogen ion. pH is 4. So I will take this anti-log. minus log of hydrogen ion. If I substitute, minus 4 is equals to log of hydrogen ion, and anti-log of minus 4 is equals to hydrogen ion, because log and anti-log cancel out each other. So if one side is log, other side it will be anti-log. What's the anti-log of minus 4? That will be hydrogen ion concentration. 0.0001. So 1 exponent minus 4, I can say. So I can also say it is 1 into 10 to the power minus 4. That's hydrogen ion. Now, what I will do, we have the formula for dissociation constant for lactic acid. It will dissociate into lactate ion. So this lactate ion is because of lactic acid as well as because of the salt. Divide by concentration of so we have Ka, dissociation constant is there, which is 1.38 into 10 to the power minus 4. We don't know the concentration of lactate ion. We know the concentration of hydrogen ion, which is 1 into 10 to the power minus 4, divided by the concentration of acid. It's given 0.15. So we'll just solve 0.15 multiplied 1 divided by. So that will be the concentration of lactate ion. So 1.38 into 10 to the power minus 4 multiplied by 0.15 divided by 1 exponent minus 4. What's the final answer for this concentration? .207. So the concentration of the ion, lactate ion, is 0.207. Now, after getting the concentration, after finding the concentration, after getting or finding the concentration, what we have to do, we have the molar mass, because the volume, as we know the formula, moles equal concentration divided by volume, but the volume is 1. So volume is 1, it means the concentration in moles will be same. So that is a concentration, but that is also moles. And moles multiplied by molar mass, that's given in the question, which is 112. So 0.207 multiplied by 112. What's the answer? .184. So 23.2, I can say, the 3 significant figure. That will be mass in gram. Is it clear? This working? A small volume of hydrochloric acid is added to a buffer solution. Explain why the pH of a solution does not change significantly. Include an equation when you refer any reaction which occur. So when we add buffer solution, the solution which resists the change in pH when small quantity of acid or alkali is added. So how we can conclude this, how we can mention this? First thing, a buffered solution, this is a buffered solution which is a mixture of weak acid is a mixture of weak acid and its salt. So what happened? Because it contained reservoir of the lactate ion, so when a small amount, and if you remember the pH of how we write the pH for, if I write the Ka, as we know, K is equals to constant, this K is equals to the acid concentration, or acid, or you can say salt concentration, hydrogen ion concentration divided by acid concentration. So if so we can say Ka multiplied by acid concentration divided by salt concentration is equals to hydrogen ion. So if this K is a constant thing, so basically if this ratio changes, then the hydrogen ion change. If hydrogen ion change, the pH of a solution will also change. But what happens if I add an acid? So the equation was, we are having this lactic acid CH3CH OH and COO. H, it will dissociate into CH3 CH OH CO and H plus. This is the dissociation of the acid, and for a salt, the sodium lactate is there, CH3CH, CH3CH is there, then OH, then COOH, sorry, COONA, this will dissociate into CH3CO, CH3CH OH COO plus Na. So if we add an acid, adding a hydrochloric acid increase the amount of hydrogen ion. When it increases the amount of hydrogen ion, the hydrogen ion react with acetate, this lactate ion, and form lactic acid. But what happened? Because already we have bulk or too much salt, so a small change like one or two molecules which are removed does not affect the balance or the ratio. That's why the pH will not change. Is it clear how this buffer solution works? Because if the ratio changes, then the pH will change. Is it clear, this part?